Good evening, everyone. Let's wait some 2-3 minutes.
Good evening, ma'am.
Yeah, good evening. So I think let's start the session. So today we will cover the week 4 content. So we will solve the problem from week 4 content. And so from this week, this week 4 is the last week for the abstract algebra. So we are completing until field, like the basics of the abstract algebra. From the next week, from week 5, you might have already gone through the contents of week 5 also. So from week 5, you will be starting the linear algebra. So let me share the screen first. Is my screen visible for everyone?
Yes.
Okay, thank you. So let's start with the what are all the concepts we covered in the last week. So in the last week, we started with the left cosec, means mainly cosecs. So we have two type of cosecs, left cosecs and right cosecs. Okay. So mostly our interest will be in the cosecs where left and right cosecs will be equal. So most examples will be like this. So in general, they need not be equal. The number of cosecs will be equal, like whatever the left coset or right coset. And so we have learned some theorems in cosecs. Okay, some theorems. I think I hope you all have gone through all the contents of the week for theorems on cosecs. And some examples also we have seen in the lectures. Okay. So after that, what we have seen is Lagrange's theorem. Okay. Can anyone state what is Lagrange's theorem? It is one of the important theorem. Anyone talking? Okay, whoever want to ask something, you can just unmute and talk. Otherwise, please mute yourself throughout the session. So, okay. What is Lagrange's theorem? It is one of the important theorem for
Subgroup.
Yeah.
Subgroup divides the main group.
Subgroup.
Order, I think something.
Yeah, if G is a finite group, if G is a finite group, and H is a subgroup of G, then order of H divides order of G. Okay, so this is the Lagrange's theorem states. This is one of the important theorem. And so after that, we have gone to normal subgroups. So what is a normal subgroup? If H is a subgroup of G, when will we say a subgroup H of G is normal? Anyone knows what is the definition of a normal subgroup? Okay, if H is a subgroup of G, we know to find the cosets, right? We are finding the left coset and the right coset. Okay, then if the left coset AH equal to the right coset HA for all A, okay, in that case, we will say H is normal. Okay, this is the definition of normal subgroup. And some theorems related to that is how to test the normality and all. We have gone through the some theorems and its proof. So using that test in this today's class, we will check one subgroup is normal or not. Like means we will use the theorem in the problems. Okay. And then I think we have covered homomorphism. Homomorphism. So I'm not going to the definition of homomorphism. Let us come to it during the problem. And then isomorphism. So isomorphism means it is homomorphism plus 1, 1 plus 1, 2. That is bijective homomorphism is the isomorphism. Okay. So next we have gone through the definition of rings. So in group, we have two operation, one group with G and an operation star. In ring, we have two operation. Usually we will say one is addition and one is multiplication. That is R plus dot. Usually we will write ring as R plus dot. That is two operations are there. So there are lots of property for R to be a ring. So you can go through the definition. I hope you know the definition already. And after that, integral domain. So I'm not going to the definition. And then fields. Okay. So these many concepts are covered in the last week. So now let's go to the questions. Okay. First question is a simple question. It is in group only. Okay. So the question is which of the following statements are true? The first statement is natural number under addition is a cyclic group. And the second statement is 2z under multiplication is a cyclic group. So we need to check if any of these statements are true or not. So anyone have any guess? Which whether first one is true or not? Not true. What is the reason? It is very simple.
Identity is not there.
Yeah, first of all, here it is given, it is a cyclic group. First of all, it should be a group. Then only we need to check about the cyclic condition. So, in the first case, n under addition is not a group. So, 1 is false. Okay. And what about 2?
Yes.
True, ma'am.
True?
Yes.
Is this a group? See the operation. What is the operation here? Here the operation is multiplication and the 2 z means,
Not a group.
yeah, not a group. Like for example, if I am taking an element 2, under multiplication, its inverse 1 by 2. Possible inverse is 1 by 2. It is not there, right? It is, first of all, it is not a group. So we now need to check about cyclic condition and all. It is not a group. So 2z under multiplication is not a group. So the second one is also false. So we got both the statements are false. Okay. Any doubt in this question? Anyone? Doubt? Okay. If you don't have any doubt, let's go to the next problem. So the second question is, again, second question, we have a set of statements to check whether it is true or not. So the given condition is H and K. These are two normal subgroups of two normal subgroups of G. So we have already seen what is the definition of normal subgroup. Normal means AH equal to HA and AK equal to KA. So the question is, which of the following is false? So I will give you a set of statements. We need to check which of them is false. HK is a normal subgroup of G. The second statement is KH is a normal subgroup. KH is not a normal subgroup of G. And third statement is H intersection K is a normal subgroup. And fourth statement is if H intersection K, that is intersection is given as the only identity element, then HK equal to KH for all H in H and K in K. Okay. So these are all the four statements. We need to check which one is false. So it is not very trivial. So we need to go through each of these and we need to see. Okay. So anyone has any idea like anything is true or anything is wrong? Can anyone tell? So I think at least the third question you can say whether it is true or correct. Anyone true or wrong?
Madam, it is true, ma'am.
Yeah, third one is true because we have already covered this in the class. Maybe I can do it once again. So we have only 3 options remaining, 1, 2, and 4. So let's go to the, okay, let's go to the first one. Okay. First of all, what is HK? How will we define the set? Not set. They are saying it is a normal subgroup. So HK is a group. And how can you define HK? Like just from the notation, you can see how it will be. I mean, you will have a guess. Correct?
Set of all HK, the product HK, H belongs to H and K belongs to K.
Correct. Set of all HK such that H in H and K in K. Okay. So this is our HK. We need to check whether it is a normal subgroup of G or not. Now, first of all, is it a subgroup? First of all, we need to check whether HK is a subgroup of G. So, what are all the conditions we need to check? We need to check the identity, means closure property, identity, inverse,
Associative property.
associative. Actually, associative we don't need to check because for any subset, since G is a subgroup, any elements in G satisfies the associative condition, like 3 elements in G. So 3 elements in HK if we are taking, then it is obviously element of G. So obviously it will satisfy the associativity. So first we will start with the closure property. I am taking 2 elements, H1, K1, H2, K2 in HK. Okay. So what we need to prove? Closure property we need to prove. Okay. H1, K1, H2, K2 belongs to HK. So in order to prove the closure property, we need to take 2 elements from HK and we need to prove it's by under binary operation, whatever the element we are getting, it should also belongs to HK. Now, since H is a subgroup, okay, before that, so what is the element here? H1, K1, H2, K2. Let's take H1, K1, H2, K2. Okay. Now consider this K1, H2. Okay. Now, what I'm saying is, since H is normal, what we can say? K1H equal to HK1, right? So this is the definition of normal. Since H is normal, for any element, we will have AH equal to HF. Instead of A, I am taking K1. So K1H equal to HK1. Okay. So, since K1 H2 belongs to K1H. Okay. This K1H equal to HK1. That means this K1H2 belongs to HK1. So what we can write? K1H2 will be equal to some H3K1. It need not be same H2. This in HK1 means for some H3, we can write K1H2 equal to some H3K1. Okay. Now I am replacing this K1H2 with the H3K1 in this expression. Okay. So what we will get? H1, K1, H2, K2 will be equal to H1, H3, K1, K2. Okay. So now we are getting an element in H, H1, H3 and an element in K, K1, K2. Okay. This definitely will belongs to HK. It is in the form HK, right? So it is in HK. So we started with the 2 elements in HK and under binary operation, H1 K1, H2 K2 is in H2. Okay. Closure property is excluded. Now, associativity is obvious. Okay, anyone is having doubt in this closure property? Is this clear for everyone? Sorry. And associativity also, it is obvious. If you have any doubt here, you can ask. Otherwise, we can go to the existence of identity. So, next thing, we need to prove that identity belongs to HK. So, can anyone say why identity belongs to HK? So, just think how identity can be written as the multiple of two elements from H and K, and note that both H and K are subgroup in G. Any idea?
E1, E2.
Not even E2, because we are dealing with only one group G. In G, one identity is there. Okay. So, since H is a subgroup and K is a subgroup, this identity will belongs to H and K. Identity belongs to K. So, what we can write E equal to E into E. Both belongs to HK. Means H and K means it belongs to HK. Okay. So, identity belongs to HK. Now, so third condition is inverse. I'm taking one element H1 K1 in HK. So, what will be the inverse of H1 K1? If it exists, what can be the inverse? H1 K1 belongs to HK means it will be in G, because HK is a subset or subgroup of G, right? So, H1 K1 is an element in G. So, element in G means it has an inverse in G. Okay. Obviously, some inverse is there in G. And the thing we need to check here is whether that inverse belongs to HK or not. If it belongs to HK, then HK is a group, right? If it does not belong to HK, we can say HK is not at all a group. So, the identity exists in G. So, I am asking about that identity. What will be the identity of H1 K1? How can I get, like, I am multiplying an element H1 K1 into some element I am multiplying here. Okay. I should get identity. So, I need to take the inverse. Inverse means I am taking K1 inverse here. What I will get? K1 inverse will go to identity. Then remaining is H1. So, I need to take an H1 inverse here, right? An H1 inverse. So, this will be identity, correct? Okay, I will explain once again. So, H1 K1, K1 inverse, H1 inverse. What will be it? Because all the operation associativity satisfied. So, I can write H1, K1 inverse into H1 inverse. Okay. This K1 inverse will become identity. H1 identity, H1 inverse. Okay. So what can I write? H1 inverse, which is again equal to identity. So this K1 inverse H1 inverse is an inverse of H1 K1. That means this inverse belongs to G. So in the other way also, we can write H1 K1 into K1 inverse H1 inverse equal to identity, and K1 inverse H1 inverse into H1 K1. That means left side and right side, both we are multiplying. Here also you can see H1 inverse H1 will become identity first, then K1 inverse K1 will become identity. So the possible inverse K1 inverse H1 inverse, we need to check whether it belongs to HK or not. Is that okay? Now to check, whether K1 inverse H1 inverse belongs to KH. Sorry. Belongs to HK because we are checking for HK. Okay. Now, this K1 inverse H1 inverse belongs to K1 inverse H. Okay. This H1 inverse is an element of H. I am considering the coset K1 inverse H. Obviously, K1 inverse H1 inverse belongs to K1 inverse H because H1 inverse in H. And by the normality condition of H, what we can write? K1 inverse H equal to what will be K1 inverse of H since H is normal? H K1 inverse. Correct? So what we are getting is K1 inverse H1 inverse equal to H K1 inverse. Okay. Now, using this condition, that is K1 inverse H1 inverse belongs to H K1 inverse, what I can write? K1 inverse H1 inverse equal to what? How can I write it as? Like as an element in H K1 inverse. Yes. It is in H K1 inverse. So there will exist some H2 or something, some H element such that it will be equal to H K1 inverse. Correct? So this is how we are writing, right? An element in H K1 inverse means that element can be written as some H into K1 inverse. I am writing it as H2 K1 inverse. Okay. Now, this H2 K1 inverse will belongs to HK because it is in the form an element from H into an element from K. It will belongs to HK. So basically what we are getting is K1 inverse H1 inverse belongs to HK. That is what we want to prove. Okay. Because this is our inverse element. We know this is the inverse from the group G. So we found that this belongs to HK. We proved that. Okay. So for any element in HK, the inverse of that element also belongs to HK. So we proved all the conditions of a subgroup. So HK is a subgroup. Okay. So our question was whether HK is a normal subgroup or not. Here we got HK is a subgroup. Is this clear for everyone? Is there any doubt? Like it may seem lengthy, but if you are just writing everything, all the details, you can simply prove it. Okay. If you have any doubt here in the proof, you can just ask now. Otherwise, we can check the normality. So, in the lectures, professor was covered a test for normality. If H is a normal subgroup of G, there exists some necessary and sufficient condition for H is a normal subgroup. So, anyone remember what is that test term? H is a subgroup. H is a subgroup of G. Then H is normal if and only if. What was the condition? Do anyone remember that condition to check the normal?
Left and right.
Yeah, left and right, that we know the definition, AH equal to HA. Other than that, as a theorem, there was a test for normality because in every case, like AH will be a coset and HA will be a coset. To check both these are same, means we need to check each and every element are like some corresponding, means same or not, means full set is same or not. So that will be a bit difficult, correct? So,
X inverse is equal to
yeah,
H.
if and only if for any H in H, X inverse belongs to H. Okay, and this should be true for all X in G. Is that okay? This is the test for usually, like while doing problem and all, we will use this condition. Now, we will come to our problem. What is our problem? HK whether HK is normal or not. So this is our question. So we need to check if I am taking some random element from HK and some element, any element X in G, whether this condition is satisfied. So I am starting with an element HK from HK and an element X in G. Okay. So we need to prove that X inverse belongs to H. HK. Okay, here our group is HK. So we need to prove that X inverse belongs to HK for all X in G. So, can anyone think about this? How can we write this? So we have two conditions given, H and K are normal. So we didn't use like we have used to prove it. We have used that to prove it is a subgroup. Here also we need to use that condition, that is H and K are normal. Okay, how can we use that H and K are normal to prove this one? Again, we will use H and K normal. Then that test for normality we will use for H and K. That means H is normal. Okay. Then X inverse belongs to H. So this is our test, right? And K is normal. Then X inverse belongs to K. Okay, for any element K, this is true. And for any element H, this is true. Now we have H and K here. So we apply this to this H and K. So what we want to prove is X inverse belongs to HK. So we should rewrite these terms in terms of these two. Then we can prove. So how can we rewrite this X inverse in terms of these two? X inverse. I need to take these two to this expression. I mean, I want to rewrite the expression so that these two expressions should be there. Then only I can use this condition, right? How can we write this? Just think about this.
HK, KH.
No, HK and KH need not be equal. Even though it is normal, this need not be equal. I just want these two conditions to be here. Okay, now I will write XH identity K X inverse. Okay, I am writing a multiplying an identity here because it is, since it is an identity, it does not matter, right? The result is same. Now, instead of this identity, can you bring any element so that I will get to these two elements?
Yes, ma'am.
X inverse.
Yeah, X inverse. X inverse or X inverse X?
X inverse X.
Yeah, X inverse X. Then only X inverse will come, right? So instead of identity, I am writing X inverse X, K, X inverse. Okay. So here I got X inverse here. Here I got X inverse. So because of this normality condition, I have this X inverse belongs to H and X inverse belongs to K. So this belongs to HK. Fine. So the element belongs to HK means HK is normal. Is the proof okay for everyone? First we proved HK is a subgroup of G and then we proved HK is a normal subgroup of G. So our first statement was HK is a normal subgroup. Okay. See, this is our first statement. So it is a true statement. We got it is a true statement. Now, what about second statement? They are saying KH is not a normal subgroup of G. Is that true or false? We proved that HK is a normal subgroup of G when H and K are two normal subgroups. Now, what about KH? Will it be a normal subgroup or not?
It's a normal subgroup.
Yeah, obviously it is a normal subgroup. Just the reverse role it is playing, right? Again, for any two normal subgroup, HK is a normal subgroup. And again, we are having two normal subgroup K and H. Then KH should also be a normal subgroup. So this statement is false. So question is to find the false statement. So we can say second one is the false statement. So 1 is true, 2 is false. Just because K and H are normal, KH is normal. Other than that, just like the proof we have done for HK, you can just reverse the roles of K and H and do the problem, means do the proof similarly. Okay. So I just want you to prove it as an exercise. Prove that. First prove that it is a subgroup and then prove that it is a normal subgroup. Okay. Now, the next statement was H intersection K is a normal subgroup. Now, this is already covered in the class. Again, let me explain very quickly. Again, we will use the test for normality. Okay. So, I am taking an element. Y in H intersection K. So, what we want to prove it is a normal subgroup. What was the test? Can anyone say what was it? So what was the condition to check the normality? XY, X inverse should belongs to H intersection K for all X. Correct? Now, how we can use that H and K are normal subgroup to prove this one? How? Yeah. Anyone? I in H intersection K. Then what does it means?
Y belongs to X.
Y belongs to H and Y belongs to K.
Okay. So Y belongs to H and Y belongs to K. Now we will use the known condition H and K are normal subgroups. So what we will get?
There exists
X,
XY,
ah,
X inverse.
XY X inverse belongs to H because H is normal. Since
XY X inverse belongs to K. Therefore, input.
XY X inverse belongs to K. These both conditions are there because K is also normal. Correct? Now, what is the next step?
Intersection. Yes.
Yeah, it belongs to H and K. So obviously, it will belongs to H intersection K. Fine. This is what we want to prove. XY X inverse belongs to H intersection K. And this is true for all X. So, H intersection K is normal. Okay, is this clear? So it is a very trivial thing to prove H intersection K is normal. Now, this is our third option, right? Now we will go to the fourth option. So fourth option was if H intersection K equals identity, only identity element is there, then HK equal to KH for all H in H and for all K in K. So among the given options, we already seen KH is not normal. That one is the wrong option, right? So obviously it will be true. One wrong option, we already got an answer. But we need to check, like we need to prove whether it is true or not. Okay, so here given H intersection K contains only identity element. And we need to prove HK equal to KH. So I will start with the HK, H inverse, K inverse. Okay. So what my plan is, I will prove this belongs to H and this belongs to K. Okay. I'm writing it as H, K, H inverse, K inverse. I can write like this, right? Because the associative property is satisfied. I'm just taking K H inverse, K inverse together and H alone. Okay. Now, H is normal. So, where does this element belongs?
H.
Yeah, this belongs to H, right? H normal means for any element X, X inverse belongs to H, where H is an element of H. So here, H inverse is an element of H and K inverse are some elements from G. So this should belongs to H, and this H is also belongs to H. So where does this element belongs? H, right?
Right.
Okay. So we can write the reason as since H is normal. Now again I can write I am taking HK H inverse together and this K inverse outside. Now can you tell where does this element belongs?
It belongs to K. H inverse is belongs to K.
Yeah, this belongs to K and this K
K
inverse.
inverse.
Yeah.
It also belongs to K.
So these two elements belongs to K means its product also belongs to K. It is since it is a subgroup, right? It is a normal subgroup is
K
used to
is
prove it is a it belongs to K, and it is a subgroup is used to say it is belongs to K. So
Yeah.
what we are getting is the same element. I am just writing it in the two different ways. Okay, the same element belongs to H and this belongs to K. That means HK, H inverse, K inverse belongs to H intersection K. Since it belongs to both H and K, it belongs to H intersection K. So what is H intersection K?
It's the inverse of HK.
No, H intersection K is given, right?
Yeah.
This is identity. Okay. So we got an element in H intersection K, but H intersection K is only identity. Then what should be this element? It belongs to this set. So it is an element in this set. So what is the element in the set? E is the element in that set. So only
Identity.
possibility is this
It's
is
identity element.
sorry.
It's identity element.
Yeah, it's identity element. So HK, H inverse K inverse equal to identity. Now what I am doing is I am multiplying with the here K H I am multiplying. Okay, both side I am multiplying KH. Here I am multiplying KH. Here with the E I am multiplying KH. E KH. Fine. So this K inverse K will be identity. And in the next stage, H inverse H will go to identity. So in this side, I will be remaining with HK. And this side, identity into KH means it is KH. Okay. So we proved that HK equal to KH. So we started with some element H and K and proved HK equal to KH. That is what the statement says. So fourth statement is also true. Is the proof fine for everyone? You have any doubt in this? Like this is just like an rearrangement and everything. There is nothing complicated. You can just go through the proof and you can try yourself. It is very easy. So if you have any doubt, you can ask. So if you don't have doubt, shall we move to the next problem? Okay. So now the problem is from integral domain and field. So, which of the following statements are true? Again, I will give two statements and we need to check which one is true. So the first statement says that a field is an integral domain. And the second statement says a finite integral domain is a field. So any guess which one is true, like anything is true or anything is false? Maybe about first one you will get very easily. Just if you know the definition of integral domain and field, you can directly say whether it is true or false. So let me just write the definition of both the integral domain and the field. Can anyone say what is the definition of integral domain? So have you gone through the videos? I mean, the last week videos?
The product of any two element is non-zero.
Not exactly, like what you are talking about is about zero divisors, I think. So first of all, integral domain means it should be a commutative ring. Okay. Should be a commutative ring. So a ring with the multiplication commutative. In a ring, always addition operation is always commutative. And if the multiplication is also commutative, we will say it is a commutative ring. Okay. And it should have unity. Okay. So I'm not going to all the definition of all these. I will just state the definition of integral domain only. Okay. Commutative ring with unity and having no zero divisor. Okay, this is the definition of integral domain. So you can just go through the lecture or like any books to check what are all these definition and what does that means and all. Now let's concentrate on the questions. Okay. Now field. Field means first of all it should be an integral domain. Integral domain. And it should satisfy the condition that a very non-zero element should have a multiplicative inverse. So from these two definitions, what we can see is if we are talking about a field, first of all, it should be a integral domain and then some extra condition is there. Okay. Now, can you say first one is true or not?
First one is true, ma'am.
Okay, first one is true because in the definition itself, we are taking field as an integral domain plus the inverse properties there. So first statement is true. One is true. Now let's go to the second statement. So here, okay, now we got any field is an integral domain. Conversely, is any integral domain is a field? No, because an integral domain plus some extra condition is a field. Okay. Now the statement is a finite integral domain is a field. Actually, this is also true. So I will just give the explanation. Like you cannot say it directly. We need a proof. Okay. Suppose let R be an integral domain. So integral domain means it will have a unity 1. Okay, with 1 unity. So we want to prove that it is a field. So the question is, a finite integral domain is a field. We want to prove that a finite, if I am taking an integral domain which is finite, I want to prove it is a field. In order to prove it is a field, what are the conditions? First of all, it should be integral domain. And the second one is every non-zero element has multiplicative inverse. So I am starting with a non-zero element. I am fixing a non-zero element. R. Okay. Now we need to find the multiplicative inverse of non-zero element only. So I am taking R star as the set of all non-zero elements. Because we don't need to consider about the zero from here onwards. And we want to prove that there exists a inverse for this element A. Okay. I am defining a function rho from R star to R star such that rho x equal to Ax. Okay. I am defining function from set of all non-zero elements to set of all non-zero element of R such that rho x equal to Ax. And here note that we know R is a finite integral domain. So R star is also finite. Because R star means R minus 0 element. Okay. Now, first I will prove rho is 1, 1. How we will start for the 1, 1 condition? How we will check the 1, 1 as? The function is defined like this. We will check 1, 1 means different elements are whether they are mapped to different images or not. If it is mapping to different images, then it is 1, 1. Otherwise, it is not. So, we will start with the image of two distinct elements. Okay. Not two distinct elements, like same image, rho x1 equal to rho x2. I don't know what is x1 and x2. I am just starting with rho x1 equal to rho x2. And by definition, it is ax1 equal to ax2. Okay. Here it is ax1 minus ax2 equal to 0. Fine. Here, this minus is actually not the usual minus. We have an operation plus here. So it may not be the usual addition. So whatever the inverse of that operation, that is mean by the minus here. Okay. Don't confuse with the just like taking other side and all. It is what I am doing is I am taking minus ax2 here and minus ax2 here. So since it is the inverse of minus ax2, it will become 0. That is what is happening here. Okay. Here I can write it as. So whatever the operation I am writing, it is like that only. Okay. To 0. Now, we know that R is a integral domain. Integral domain means, I already told, it does not have a zero divisor. That means AB equal to 0 implies either A equal to 0 or B equal to 0. This is the meaning of no zero divisor. Okay. So here A x1 minus x2 equal to 0. Okay. So A is non-zero. Correct? So this x1 minus x2 should be equal to 0. Sorry. Okay, let me repeat once again. AB equal to 0. If A not equal to 0 or B not equal to 0,
MP should be 0.
and B not equal to 0, means if we are having two non-zero elements, but their product AB equal to 0, in that case it is a zero divisor. Okay. Here in the integral domain, it does not have a zero divisor. So if we are writing the product equal to 0, one of the elements should be equal to 0. Okay. Either A should be equal to 0 or x1 minus x2 should be equal to 0. Clear? But we started with the A non-zero element. A is a non-zero element. So this is not possible. Okay. So what we get is x1 minus x2 equal to 0. Or x1 equal to x2. Fine. So what we started is rho x1 equal to rho x2. And finally we are ending in x1 equal to x2. So this means that rho is 1, 1. Okay. So what we are getting is rho is defined from a finite set R star to the same set R star and rho is 1, 1. So that means distinct elements in R star have distinct images in the R star. Okay. So it should be on to also. So rho is on to, since R star is a finite set. That means in a finite set, if we are able to prove one of the condition, either 1, 1 or on 2, then we can say the function will be satisfy the other condition also. Means here we proved rho is 1, 1 on a finite set. So rho will be on 2 on a finite set. You can check the proof if you want. It is very simple. So rho from R star to R star is a bijection. Okay. So what we are getting is rho is a bijection. So since rho is a bijection, what I can say is for 1 in R star, okay, I am taking 1 from this R star. Okay, so there exists exactly one element, that is one and only one element in this R star such that rho is mapped to 1. Okay, sorry, that element is mapped to 1 under rho. That means there exists x in R star, that x will be unique. X in R star such that rho x equal to 1. So what is our rho x? By definition, it is Ax. Okay. So we started with an element A. Okay. And we got an element x is there such that Ax equal to 1. So what we can say is x is a, because 1 is the unity. 1 is the unity means it is the multiplicative identity. So for A, we got an x such that Ax equal to 1 means x is the multiplicative inverse of A. X is the clear. So we started with an element, any element A, it has a multiplicative inverse, which is a non-zero element. So, if it is a finite integral domain, we are able to find like this. So, we got a this. R is a field. Already given it is an integral domain, we proved the multiplicative existence of multiplicative inverse also. So, integral domain plus the inverse under multiplication. That is the definition of field. So, both the conditions are satisfied here. So, R is a field. Okay. So, that statement, the second statement is also true. So, it may seem difficult for you now, but just go through the questions and just go through the lectures and all, like just understand the concept very thoroughly. Then it will be fine for you. It's not that difficult. And in between, any doubt, please ask. Because from here, like we are stopping. I mean, from this week, the abstract algebra is over. Next week, means from week 5 onwards, the linear algebra is starting. So it is just the basics of abstract algebra. So you don't need to go to very higher levels and all. Just go through the videos and understand the concept. So shall we go to the next problem then? Any doubt? Anyone? Okay, someone asked about like where to get these videos. These videos actually, I think you might have already gotten some drive, like some Excel sheet or something where the link of these videos and the notes are all available. So you can check. I mean, I'm already uploading everything in the YouTube and I am providing the links also. I think it's already shared with you. So anyhow, you can just search the NPTEL Introduction to Abstract and Linear Algebra in YouTube also. You will get the video. So now let's go to a simple problem. So we know Sn. What is Sn? Do you remember Sn? Anyone? What is Sn? So last week we talked about Sn like
Symmetric group of degree n.
symmetric group on n letters. Means symmetric group means set of all permutations on a set of n elements. That is the symmetric group means. Okay. Now, okay, so n letters means 1, 2, 3, etc. n. So, what are the order of so two permutations are given here. So the question is to find the order. Okay, let me give the options also. For 2. Okay, so you can see the two permutations F and G. So can anyone say what is the order of F and G? What is the option correct answer? Maybe the order of G you can, actually both the order you can say very quickly. Just take 1 or 2 minutes and just very quickly go through the F and G.
I guess it is 4-2, madam.
Yeah, 4-2. So the thing is, to find the order, we need to find F, F composite F, F composite F composite F, etc. At what n, what least n, such that F power n becomes identity, that n is the order. Okay. Now, first let's start with the G. Okay, G is a bit simple. G equal to, if I am writing it as a cyclic notation, G 1 is going to 1, 2 going to 3, and 3 going to 2. So, in a cycle, we will write it as 2, 3. 1 is fixed, so we don't need to consider about 1. So, only 2, 3. So, G is not identity. G composite G will be identity. Because in G composite G, first 1 will go to 1 and then again 1 will go to 1. And 2 will go to 3. In the next G, 3 will go to 2. So finally 2 is going to 2. And 3 is going to 2, 2 is going to 3. Okay, 2 times G apply. So each element, 1 is going to 1, 2 is going to 2, 3 is going to 3. So G composite G is identity. So order of G is 2. Okay. Now, this F also we can write it as a only one cycle. So, can anyone say what is the cyclic representation of F? Just like this representation.
One, 3, 2,
Yeah,
4.
1, 3, 2, 4. Okay. Because first 1 is going to 3, 3 is going to 2, 2 is going to 4, 4 is going to 1. That cycle ends there. Means starting with the 1, ending in 1. Okay. So 1, 3, 2, 4 is the cycle. And 5 is fixed. So we don't need to write it about that. So if we are getting only one cycle, to find the order, it is easy. Order will be the same as the length of the cycle. Okay. So here order of F will be, order of F will be equal to 4. So why I am saying like this is because 4 times F we are applying, what will happen? First time 1 will go to 3. Second time it will go to 2. Third time it will go to 4. And the fourth time it will go to 1. So in the fourth time 1 is going to 1. In the same way, first time 3 is going to 2 and 2 is going to 4. Then to 1 and the fourth time again it comes back to 3. So the 3 is mapping to 3 if we are applying F 4 times. The same happens for 2 and 4. And 5 is mapping to 5 always. So whatever the times applied, 5 will be mapped to 5. So 4 is the minimum possibility such that F power n equal to or F composite F composite F composite F equal to identity. Okay. So this is very simple question. We have already seen this kind of question in last week also. So again, if you have doubts here, you can ask. Otherwise, we can move to the next problem. Any doubt here?
No, ma'am.
Okay. Now let's go to one question from homomorphism. So we have already seen what is homomorphism. So the question is, Okay, just wait, let it come. Okay. So the question is, given that F is a homomorphism from Z plus 2 R plus dot. So here we should note the operations here. In the Z, it is the operation addition, and in R plus it is the operation multiplication. And given the value of F at 3 as 1 by 3. So the question is to find the value of F at 9. We just know that F is a homomorphism. Using that, how can we find the F of 9, or what will be the answer? Just apply the definition of homomorphism and given condition F of 3 equal to 1 by 3. Anyone knows the answer, or just how to approach the
Ma'am, option A 1 by 27.
Yeah, option A. So can you just explain how you got the answer?
Madam, because f of 9 can be written as f of 3 plus 3 plus 3.
Yes.
The left side is the domain is the addition operation.
Hmm.
The go domain is the product operation. So
Yeah.
it is a homomorphism.
Yeah.
So f of 3 plus 3 plus 3 is f of 3 into f of 3 into f of 3.
Correct.
But f of 3 is 1 by 3.
Yeah.
So it will be 1 by 3 into 1 by 3 into 1 by 3. So finally it is 1 by 3 power 3.
Okay.
So answer is 1 by 27.
Correct.
Correct?
Yeah, correct. So I hope everyone understood his explanation. So we are just applying the condition F is a homomorphism and F of 3 equal to 1 by 3. So we know that F is from Z under addition to set of all positive real numbers under multiplication. Okay. And F is a homomorphism. So what we are having is F of 9. Okay. That means 9 is an element in the Z. Okay. And in Z, we know plus is the operation. And we know the value of F at 3. So 9 we will write in terms of 3. Okay. So the possible writing is F of 3 plus 3 plus 3. Because 3 plus 3 plus 3 is 9. And plus operation is in the Z. And the value of F of 3 we know. And then we are using the homomorphism condition. What is homomorphism? F of x star y equal to f of x dot f of y. Star is the operation in the domain and dot is the operation in the codomain. Then we will write like this. So here f of 3, f of 3, f of 3. So like here 2 elements or 3 elements, it does not matter. So what is f of 3? It is given 1 by 3. So 1 by 3 into 1 by 3 into 1 by 3, which is equal to 1 by 27. Is this clear for everyone? So yeah, like that one problem, obviously there will be in your assignment also, I hope. So this is just apply the definition. So I think it's clear. Any doubt here? Okay. Now again, one question. So a map is given. Okay. So the map is given from int to even. Int means set of all integers under the operation addition. Again, even means set of all even integers under the operation addition. And the function is given as f of x equal to 2x. So the options are f is not 1, 1. F is not on 2. F is an isomorphism. Okay. So, can anyone say, okay, about 1, 1 and on 2, actually we can say very quickly. F is a map from integer to even. We need to check whether it is 1, 1 or on 2. How we will check 1, 1 as? We will start with the f of x1 equal to f of x2. Okay. So, if we are able to prove that x1 equal to x2, it is 1, 1. So, f of x1 equal to f of x2 implies, what is the definition? F of x equal to 2x. That means 2x1 equal to 2x2. Okay. So, here the, like, multiplying with the 2 means the usual multiplication. Okay. So, the 2 we can cancel from both sides. This implies x1 equal to x2. Okay. So, f is 1, 1. Okay, we start with f of x1 equal to f of x2 and ending in x1 equal to x2. So, f is a 1-to-1 map. So, this is very simple to check f is 1, 1. Now, to prove that f is on 2. First of all, what do you think whether f is on 2 or not? F is defined from, see the question, from integer to even integer such that f of x equal to 2x. Is this on 2?
Yes.
Yes. On 2 means for any even integer, there should exist an element in integer such that f of x should be equal to that even integer. So, I will, to prove the on-to-ness, we should start from the element from codomain, okay? An element y in even integers, okay? Since y is an integer, even integer, what we can write? Y equal to 2x. Okay. And x will be an integer. Since it is an even integer, it will be in the form 2n or 2x, where x is an integer. Okay. Now, what will be f of x by definition? So, for this x, I am applying f of x. So, this f of x by definition, it is 2x, which is equal to our y. Okay, 2x equal to y. So, f of x equal to y. So, f is on 2. So, we got f is 1, 1 and on 2. So, for both the options, A and B are false. Not 1, 1, not on 2. These two are false. Now, we need to check the isomorphism. So, what is isomorphism? In the beginning, we started with the isomorphism. I mean, we have gone through the definition of isomorphism. So, do you remember what is the definition of isomorphism?
I of x1, x2.
Yeah. Isomorphism means, first of all, it should be a homomorphism and it should be 1, 1 and on 2. 1, 1 and on 2 we already proved it. Now we need to check the homomorphism condition. Okay. So, how can we check the homomorphism? Can anyone tell?
Phi of x1, x2.
F of, what is the operation here?
F of x1, x2.
Not x1, x2, right? The operation is addition, additive group of
X1 plus
integers. So, yeah, here both the integer and even integer, both are in the additive sense, okay? So, f of x plus y should be equal to f of x plus f of y. This is what we want to prove. Okay, f of x plus y should be equal to f of x plus f of y. Okay. So we will start from the left side, f of x plus y. What is the definition of f of x plus y?
2 into x plus y.
Yeah, 2 times x plus y. So simply we can write it as
2x plus
x
2.
plus 2y. And this is nothing but
Phi
f
of
of
x.
x plus
F of x.
f of y. So, okay, let it come 1 minute. Okay, so we got that f is a homomorphism also. So we prove f is a homomorphism 1, 1 and on 2. So f is a isomorphism. So this is the third option. So the third option is correct. Okay, any doubt here in the last question? Okay, then I think we will do one more question from the homomorphism. The question is, so the first map is given as, it is from Z to RL. Okay, it will come in 1 minute. Where Z and R are defined under addition. Okay, and it is given as phi 1 of x equal to x. So this is very simple question. So what do you think, whether it is a homomorphism or not? Is this a homomorphism? Can anyone answer? Okay, let us check then. Phi 1 of x plus y should be equal to phi 1 x plus phi 1 y. That is the only condition we need to check. Okay, and here both side the operation is plus. So we can use plus in both operation, like both sides. So under the definition gives phi 1 of x equal to x. So phi 1 of x plus y will be equal to x plus y. So what is x? X is phi 1 of x and y is phi 1 of y, right? So it is nothing but phi 1 of x plus phi 1 of y. So this is a homomorphism. Any doubt in this one? This is very simple. Anyone has doubt? Then you can ask. Otherwise, we will go to a kind of a bit non-trivial example. So the map phi 2 is defined from the set of all real numbers to set of all integers under addition. Again, both the operations are addition here. And phi 2 of x equal to greatest integer x. So you know what is greatest integer x, right? So if I am taking any real number, the greatest integer less than or equal to that real number is the greatest integer function. For example, what will be the greatest integer of 1.2? The greatest integer which is less than or equal to 1.2 means we will take all the integer less than 1.2 and out of that which one is the greatest one? What is the greatest integer of 1.2? Do you know the answer or greatest integer of 1.2? It is 1. Okay. Do you know the greatest integer function? Hello, am I audible? Am I audible? Can anyone respond? Okay, okay. So I hope you have doubt with the greatest integer. Okay.
Phi 2 of x, ma'am. Phi 2 of x equal to something. What is this, ma'am?
Okay, that is what I'm saying. Greatest integer of x. Do
Okay,
you know
okay.
what is the greatest integer function?
No, ma'am.
Okay. So greatest integer function means if I'm just like it is a function on the real line. I'm starting with I'm taking any real number. So then I will collect all the integer less than or equal to that real number, and among those real number, what is the greatest one? That will be the greatest integer function. Or in simple word, if I am saying, suppose I am taking a real line 0, 1, 2, minus 1. Okay. If I am taking a number here, okay. So the integer number just below this number is the greatest integer of this number. Okay. Here the integer just below it is 0. Okay. So what actually says is we will collect all the integers below this blue point. That means 0, minus 1, minus 2, everything we will collect. Out of this, what is the greatest one? That it is 0. Okay. So greatest integer of this one will be 0. So what will be greatest integer of 1.2? 1.2 will be somewhere here, right? Okay. Will be somewhere here. So the integer less than this is 1. Okay. So greatest integer of 1.2 will be 1. So what will be the greatest integer of 0? 0 itself is an integer. So the just number, the integer just below, or just below means the greatest integer below 0 is 0, right? Below means including 0. Okay. So whatever the integer point we are taking, the greatest integer of that integer will be itself. Okay. So greatest integer of 0 will be 0. Now, can anyone say greatest integer of minus 0.5?
Minus 1. Minus 1.
Okay, minus 1. So this is how the greatest integer function is formed. Okay. Now, the question is, I am defining phi2 as phi2 of x equal to greatest integer of x. And the operation. both
It's
side of-
0 only, no? Minus 0.5 is 0.
No. Where will be minus 0.5 will come?
Because
right?
the, yeah,
So the number, we will consider all the integer below this. Okay. 0 is greater than minus 0.5. So this side we will not consider. From here, we will consider the left side, minus 1, minus 2, etc. So
Okay.
minus 1 is the integer among all these, like the greatest integer among all these, which is below minus 0.5. Fine.
yes, ma'am.
Okay, that is why it is minus 1. So that is the definition of the function. So the function, like here also we can see, it is defined for all real number, but its range is going to only z. So we are considering this function. So the operation is here addition. So r plus and z plus is the group here. And phi2 of x is greatest integer of x. So now, can anyone say whether this phi2 is a homomorphism or not? So the condition we need to prove here is phi2 of x plus y equal to. So we don't know whether it is true or not. If it is true, it is a homomorphism. Sorry. So, okay, will it be satisfied? Like you can just try with some example, just think a bit and think whether phi2 of x plus y will be equal to phi2 of x plus phi2 of y. Okay, maybe I can give a hint like that. It is not true. Okay, this equality will not hold actually. Now, can you find such a number x and y such that this is not equal? Okay, let me write one more step. By definition, phi2 of x plus y is greatest integer x plus y, and phi2 of x is greatest integer x, and phi2 of y is greatest integer y. So can anyone find such that this equality does not hold? Some x and y you can find. Like there are so many possibilities, some possibility.
Minus 0.5.
Can you repeat again?
X minus 0.5
X
minus 0.5.
okay. And y?
Y is equal to plus 0.5.
Plus 0.5. Okay, just let us check this, whether it will work or not. So here x plus y is minus 0.5 plus 0.5. That means it is equal to 0. greatest integer of 0. 0 is an integer, so greatest integer of 0 is 0 only. So greatest integer of x plus y equal to 0. And what is greatest integer of x? Greatest integer of x is greatest integer of minus 0.5. Okay. So greatest integer of minus 0.5 will be minus 1. And what is greatest integer of y? Greatest integer of y is 0.5. So greatest integer of y is 0. Okay. So here it is not equal. Greatest integer of x plus y not equal to okay. Here greatest integer of x plus y is 0, but greatest integer of x plus greatest integer of y is minus 1. So this is not a homomorphism. Is this example clear for everyone why it is not a homomorphism? Any doubt in this question? If you have doubt, you can ask. Otherwise, let's move to the next problem.
Y is taking as a plus value, ma'am, 0.5, and y minus x value is taking as minus 0.5.
So why we are taking is we need to check whether it is a homomorphism or not. So
Oh,
if it is a homomorphism, this equality should be there. Greatest integer x plus y equal to greatest integer x plus greatest integer y. So we should go through some possibility, like some examples we can try. So at some cases we are not getting this is equal, like the inequality is coming here. Okay. This is not just minus 0.5 and 0.5. You can try, for example, x equal to y equal to 1.6. You can try. Try that.
okay.
So many possibilities are there. So we are just finding some number x and y such that it is not.
Okay, taking any number,
Any number.
we can check. Okay, thank you.
So again, I have a map from phi 3 from R to R star. And here R is additive. R star means set of all non-zero elements in R. And it is under multiplication. Okay. And it is given that the function is defined as phi 3 of x equal to 2 power x. So let's check whether it is homomorphism or not. So what do you think, whether it is it homomorphism? The thing we need to prove is phi 3 of x plus y.
Yes, ma'am. It is homomorphism.
Yeah, it is homomorphism. So let's just write it formally. So phi 3 of x plus y is by definition 2 power x plus y. Okay. So 2 power x plus y, we can write it as 2 power x into 2 power y. So this is the, like how we separate 2 power x plus y as 2 power x into 2 power y. And under multiplication, like here R star is under multiplication. So here this we can write it as phi 3 of x into phi 3 of y. Okay. Here the domain is under addition and range is under multiplication. So accordingly, we have to take the operation in both sides. So phi 3 of x plus y we are getting phi 3 of x into phi 3 of y. And hence phi 3 is a homomorphism. Okay, so like that, so homomorphism checking is now it is fine for you, I think. So you can just go through some exercise again if you want. Now a question. So we need to check true or false. I will give one statement. We need to check whether it is a true or false. Okay. So the question is, we have given a ring Z5. Z5 means set of all elements from 0, 1, 2, 3, 4. Okay, the operations are addition and multiplication. Whether it contains divisors of 0 or not. So this is the question. So can anyone say what is the, like, whether it is true or false?
Ma'am, it is true, ma'am.
It is true. So,
Yeah.
yeah. So, first of all, we should know what is the meaning by divisors of 0. Then we can check whether there exists a divisor of 0 or not. What is the divisor of 0? No, it's like some non-zero element AB such that AB equal to 0. Okay. Okay. So if there exists some AB from Z5 other than 0 such that A into B equal to 0, like under this multiplication operation, AB equal to 0, then we can say that that A or B is a 0 divisor. Okay. Now, can we find any such element here? No, right? If I am taking any two pair, like 1 into 2 is 2, 1 into 3 is 3, it is not 0. 1 into 4 is 4, it is not 0. Basically, what here happens is, it is Z5. If two element is multiplied and it becomes 0 means, it should be a multiple, like if I am multiplying two element, I mean, suppose A and B are here such that AB equal to some 15 or something, then it will become 0 here, right? But no two element, if I am multiplying, it will not become a multiple of 5. Okay, so you can just try with each pair, 1 into 2, 1 into 3, 1 into 4, 2 into 3, 2 into 4, 3 into 4. Everything becomes a non-zero element here. Okay, nothing is a 0. So Z5 has no divisor of 0. So the statement is true. Anyone is having doubt here? It is just like we are just applying the definition. Any doubt? So if no doubt, we can do one more question on the divisors of 0, because okay, so the question is, to find the divisors of 0 of Z8. Z8, you know, the element from 0 to 7. Again, under usual addition and multiplication. Can anyone say what are all the possible divisors, 0 divisors of Z8? If you
2,
can.
4, 2, 4.
2, 4. Any other?
1, 8.
8 is not there.
No, 8 is not
No,
there in Z8.
Okay, okay.
3,
2 and 4 is there because 2 into 4 equal to 8. And obviously that is 0 in Z8. You can think about the multiples of 8 also. If 2 element multiplied and if we are getting a multiple of 8, again it will be 0 in Z8, right? That kind of elements like pairs also you can consider. So one possibility I am taking 2 and 4. Any other possibility? If we are taking 4 and 6, 6 into 4 is 24. And 24 is again 0 in Z8, right?
yes.
So multiple of 2 elements, 2 non-zero elements from Z8, but its multiple is 0 in Z8. 2 into 4 is 0, 4 into 6 is 0. So in the same way, you can find each of the pair actually. So whatever the pair, like you can try everything. So here we will get only these 3 elements of the 0 divisors. Two, 4, and 6. Okay. Is that fine for everyone?
Yes.
Is there any doubt in this?
No, ma'am.
Okay, good. So, yeah, we have just gone through like almost all concept, I think. So from next week, we will start the linear algebra. So I think let's stop it today. Or do you want to solve some more questions? Or maybe from posits, I think I haven't done anything. Okay, just one more question we can do and then we can stop.
No, give
Yeah.
an example of a group and a normal subgroup of it. An example.
An example?
A normal subgroup of a group.
Okay, example of a normal subgroup. So that's like if you are taking any abelian group, then any subgroup will be a normal subgroup. For example, I am taking Z. Okay, Z is our main group, and 2Z as a subgroup of Z. Okay. So here, just using the definition, we can say 2Z is a normal subgroup of Z. Here, what are the left posits of 2Z? So, what are all the possible left posits of 2Z? One is 2Z and the other one is 1 plus 2Z, right? 2Z means it will cover all the even integers. Now I am adding 1 with it, 1 plus 2Z. 1 plus 2Z means I am adding 1 with each of the even integer. So it will cover all odd integers. So 2Z and 1 plus 2Z all together becomes Z. Okay. So the left posits are One is we can say 2z or 0 plus 2z and 1 plus 2z. Okay, now coming to the right causes. So what are all the right causes here? Again, 2z plus 0 will be one right coset. Right coset means in the right side we are adding the element. Okay. And 2z plus 1. Again, 2z plus 1 means each even integer we are adding 1. Okay, so it will cover all odd integers. So here I am just representing the coset like this. Instead of this, you can write 3 plus 2z also. Okay, so to say it is normal, what we need to prove is a plus 2z equal to 2z plus a. Okay.
Okay.
So if a is an even integer, what will be a plus 2z? Means with the 2z, I am adding an even integer always, like one particular even integer. So again, it will cover full even integer, right? So if a is even, a plus 2z equal to 2z. But it is same as 2z plus a. Because whatever, if I am adding right side or left side, it does not matter because the operation addition is the commutative operation here. So if a plus 2z I am taking or 2z plus a I am taking, both becomes the full 2z. In the same way, if I am taking a as an odd integer, what I will get? A plus 2z equal to 2z plus a equal to set of all odd integer. Means I am adding an odd integer with each of the even integer. So I will cover all the odd integers. In the same way, if I am adding from left or adding from right, whatever the final thing is, what I am getting is set of all odd integers. Correct? So the operation is here commutative. So this commutativity makes the whatever the subgroup I am taking here, it will be a normal subgroup. Okay. So in an abelian group always, whatever subgroup you are taking, it will be a normal subgroup. Is that clear? Is this example clear?
Okay.
Okay. Okay, then I think let's stop. If you have doubt, you can ask. Otherwise, let us stop the session. So this is how you can find a cosets also. So any other doubt from anyone?
Madam, one more doubt, ma'am.
Yes.
Madam, in a group of ln of z, the linear group,
Linear group means
G ln of z,
general linear group. Okay, okay, yeah.
yeah, general linear group. A subset is a collection of the matrix such that the determinant is in the form 1 by something, 2 power n.
Okay.
Can you say that what about this subgroup? It is normal or cyclic?
It will not be a normal subgroup, I think.
How to check, ma'am, on this condition? Commutative,
Is this a question from assignment?
ma'am?
Is this a question from assignment?
Yes, madam. This is a model question, ma'am.
No, I'm asking about, is this a question on the graded assignment?
Yes, ma'am. Yes, ma'am.
If it is a question from, I think, yeah, then I cannot solve this question actually.
Okay, madam. How to find out that this is commutative or how to check the condition, ma'am?
First, the question is whether it is normal or not, right?
Yes, ma'am.
So, normal means either you can check like the condition for normality, test for normality is there that we have mentioned in the class, and the professor has also taken. Either you can check that. Okay.
Madam, the determinant condition satisfy, ma'am. The determinant of AB and determinant of BA are both are equal, ma'am.
Means that does not matter. Like what I'm saying is, if for some element, random elements, if you are saying AB equal to BA, not that one. I mean, in general, if H equal to HA, so if some particular H I am taking from HA, and for that H equal to HA, then that we cannot what H equal to H, that may not be possible always. But it is possible that A into capital H, the subgroup H equal to the subgroup H into A. Okay.
Okay.
That is possible. So the thing is, one, you can use the test, or you can just like try AH equal to HA or not.
Okay, ma'am. No, ma'am.
Hmm.
The condition for the determinant will satisfy for any matrix belongs to this group. Determinant of the AB is a determinant of BA. Both are equal. We can say this is a commutative.
So, what is
My-
the like definition of commutative under multiplication? AB should be equal to BA, right?
BA. But the determinant of AB is equal to determinant of BA. This only satisfies the group.
How can you say just because of determinant of AB and BA that like?
Because it is a collection of the group, collection of matrix such that the determinant is 1 by 2 power
That
m.
is fine, but still AB should be equal to BA. Then only we can say commutative. You just try with some example, AB equal to BA or not. It will not be true always, right? Like the determinant does not matter. AB, the matrix AB and matrix BA are equal or not.
Okay.
So just go through the question. I cannot like I should not explain. Okay. Yeah. So anything else? Okay, then I think no other question. Shall we stop the meeting? Okay, let me stop share. Okay, then. So thank you everyone for attending. Let's meet the next week.
Thank you, ma'am.
Yeah, thank you.